In the next section, I want to introduce suffix arrays, which will be a way to work around this massive space usage of suffix trees, the large constant in the linear term. And to motivate that, let's start with the suffix tree. So here again, tilted to the right, or tilted on the side. And I wrote it so that for every node, the child edges are sorted alphabetically. We assume that the end of word marker is smaller than all the real characters. And then comes A before B before N, and at the other nodes as well, B before N, and so on and so forth. If you do that for every node, you notice that the leaves give you the suffixes of that string in sorted order. Just by the construction of the tree, that has to be that way, if we sort by alphabetic order the children in each node. So one could say, well, if this tree with all its pointers and so on is too heavy to store, maybe we can forget about the tree and just store this sorted list of suffixes. And I want to point out that maybe some things are lost. Some things will be lost, but we'll come back to that. While some things are lost, not everything's lost. You can still do string matching, or the string indexing problem. So you're given the text, you compute this. Now I give you a pattern. Can you tell me whether it occurs in the text and where? The answer is yes, because you have a sorted list of things and you try to find something else in that sorted list. Not exactly, but you try to find if that is a prefix of one of these strings. So you can do something like a binary search. Let's do this on this example just to illustrate that point. So we have Anna. Okay, I'll probably have to write indices so I don't make mistakes. We have 10 elements initially. Binary search starts by jumping to the middle. Let's take a middle rounded down as this one. So we compare with Anna. And let's say we use the normal order in dictionaries, where a word that ends before another one comes earlier in the alphabet. So we say Anna is smaller than an Anna Ben. So we want to resolve this direction. Now we have these, and again we pick the middle, say this one. We compare with Anna. This time it's bigger, so we move down. And then another comparison here. We would find Anna is smaller. So if we wanted to insert Anna in this sorted list of strings, it should go into this gap, right? That's binary search. So what have we won from this? We know if there's a string that starts with Anna, it has to come right after this position. And so we go one step down and check if this string starts with Anna or not. And in this case it does, which means we have found an occurrence of our pattern. Okay? We can also find all occurrences of the pattern if we do a second search, where whenever we find a word that has Anna and then something else, we say that is smaller. So we start here again, but this time there is Anna. So we go down. Then, well, whatever, we will probably take this one and decide Anna comes earlier. And then this one, Anna comes earlier. So the blue one gives us this one. That's the position where you have to insert Anna if we put shorter strings after all the ones that have this as a prefix. So again, you could take one step up and find, okay, there's Anna again. In this small example, there's really just these two. In general, this will be a whole range, and it will be all the occurrences of Anna in the whole string in the text. So with 2 binary searches, you find not just one occurrence or the fact that there is none, you actually find all occurrences in a neat, compact representation. All the indices listed there. That's the part that we can still do. Now, we don't really want to store a list of strings. As in the suffix or a tree, that would be space inefficient. But the same solution as in the suffix tree is we just store the starting index of a suffix instead of the string, and we keep the text around separately. And this is it. So this list of starting indices of the suffixes so that the suffixes are in sorted order, that's called the suffix array. So this beast here. Here's formally defined again what that should mean. So the rth element in the suffix array, L of r, is the starting index of the rth smallest suffix in lexicographic order. And you have to again pay attention that we start at 0 and so on. If you work out what the binary search costs, then we need log n plus at most 2 for the binary search. But each of the comparison costs us m character comparisons if that's the length of the pattern, because we have to do a string comparison in each point. So the number of symbol comparisons is a bit more expensive. That's how we compare all the time, string matching algorithms and so on. So that's the fair measure. So it's not quite as good as suffix trees, where we had only the m part. There was no dependence on n in tries, remember? At least assuming that we can go from one node to a child in constant time. So suffix arrays are a bit slower. They have this log n factor in here. But log n is fairly small. I mean, n is an exponential reduction in the time compared to a linear scan. That's often good enough. Even if n is in the billions, log n is just 30.